Okay, let's start the analytical portion of the online class exercise number 6 on chapter 7. The first one is an example that here you have a drive-through bank. Okay, in a drive-through window in a bank, the arrival rate is 15 and the service rate is 20 per hour. So what model would you think of? It is not a constant service rate because this 20 per hour or 20 customers per hour of service rate, it is an average. It is not constant. So this is a single channel, which means you're talking about model number 1. Okay, so this is model 1. So now we can calculate using the figure or the figure that I talked about. If you go to the book, there is a figure which is, I believe it is 711, and the model equations are given there. The waiting line model equations are given there. So for model 1, the equation is going to be, what is the average utilization of the teller? When you want to find the utilization of the teller, that is the same as rho, which is lambda over mu, which is going to be equal to lambda, which is 15, divided by the service rate 20, and that is 0.75, or 75% is the utilization rate. Okay. Now let's calculate all the waiting line model equations. The first one is average number of customers waiting in line. That is going to be equal to LQ. So LQ is going to be equal to lambda square, which is 15 times 15, divided by mu, which is 20, times mu minus lambda. And I'm going to put the parenthesis 1 over here and 1 over here. And that comes to 2.25. Now, you cannot have a quarter person there, so I'm going to round it up. So I can use a round formula, and the round formula of 0 decimal points, and that gets me 2. What is the number of people in the system? Average number in the system. The system is going to consider, of course, the service rate as well as the arrival rate. So the system is going to be LS. The average number in the system is LS, which is going to be equal to lambda, which is 15, divided by mu, which is 20, minus lambda, which is 15, and that comes to 3. So there are 3 people in the system and 2 people in the line. Okay, let's find the average waiting time in line. For model 1, the waiting time in line is WQ, and that is going to be equal to LQ over lambda. LQ is the one that you calculated, which is this 2, divided by lambda, which is 15, and that comes to 0.13. And you can make this to different decimals and things like that. Maybe the best thing is probably 2 decimals. That's what we look for. So let's go to home. Here we can actually, if you go here, you can decrease the decimal to 2. and this is per hour. So the waiting time is 0.13 hours, which is actually going to be equal to 0.13 times 60, and that is 8 minutes. WS, on the other hand, is going to be equal to LS, which is 0.13, divided by lambda, which is 15, and that is 0.00, all these 889, and so I'm going to click on this again, do for 2 decimal points, and that is 0.01 hours. Let's make sure whether this is right. LS, so LS is, no, I made it a wrong thing. So this is going to be equal to LS, which is 3 divided by lambda, and that is 0.2 hours. Now this is correct. So LS over lambda, not WQ over lambda. Okay, so WS is going to be equal to LS over lambda, which is going to be LS is 3 and lambda is 15. That comes to 0.2 hours, and that will be equal to 0.2 times 60, and that comes to 12 minutes. So the average waiting time in the system is 12 minutes. That means from the time a person enters the bank until he leaves, it's going to take 12 minutes on an average. Okay, so this is your first model. Let's focus on model 2 next, which is problem 3. In model 2, we're going to be looking at this problem. So the Heart Association plans to install a free blood pressure testing booth. Previous experience indicates that 10 persons per hour request a test. The arrival rates are distributed in a Poisson way, and the blood pressure measurements can be made at a constant time of 5 minutes. So when you talk about service being constant, that is going to be model 2. So we know that. The arrival rate is 10. The service rate is 12. How did you get that 12? The 12 is you have 5 minutes is the service rate. So 60 divided by 5 is going to be 12. That's how I got the 12. Let's find LQ, LS, WQ, WS. For model 2, if you go to the same figure 711, you get the first one is going to be equal to LQ. LQ is going to be lambda squared, which is going to be 10 times 10 divided by 2 times mu, which is 12, times mu minus lambda, which is 12 minus 10, and that is going to be equal to, something is wrong here. Let's see what is wrong. I have to make sure that this is within parentheses, and that comes to 2 customers. Okay, LS is going to be equal to, according to figure 711, LS is going to be equal to LQ, which is 2, plus lambda over mu, which is 10 divided by 12, and that comes to about 2.91, and I'm going to bring it to make it equal to 3 customers. WQ, on the other hand, is going to be equal to, for model 2, WQ is LQ over lambda. LQ is 2 divided by lambda, which is 10, and that comes to 0.20833, and that comes to about 12.5 minutes. And how did I get 12.5? I simply multiplied it by 60 because 60 minutes per hour. WS, on the other hand, is going to be equal to LS, which is going to be 3 divided by lambda, which is going to be 10, and that comes to 0.291667, and that comes to 18 minutes. I can make these into as less like that, into for 2 decimal places, and I have the answer. Let's go to model 3, and we'll also discuss why it is model 3. A parts clerk fills a request while the mechanic works. Mechanics arrive at a rate of 40 per hour, okay, which is given to you. Clerks fill requests at the rate of 20 per hour, which is also given to you. 40 is my lambda, 20 is my mu. The cost of hiring a clerk is $30 per hour. The cost of mechanic waiting in line is $60 per hour. We need to find the optimal number of clerks to staff the counter. Okay, in a parts, in a bin, usually the clerk has to do many things. He has to first get the request, go through the request, get the part, get the signature from that person. So different operations are done. So this is a multiple channel, which basically means that it is going to be a model 3. So we know it is model 3. So the first thing that I want to do is to find LQ. Now, how many clerks should be there? That is a question. So if I have one clerk, the arrival rate is 40, but the service rate is 20. So if I have only one clerk, it is impossible for that one clerk to do the job. Let's say if I hire 2 clerks. If the 2 clerks, basically the arrival rate is 40, and the service rate is 2 times 20, which is 40, which is very equal. And sometimes it's not, this is an average. So it may not be the correct number of clerks. You need more clerks. So you need at least 3. So I'm going to start with 3. See, that is the argument that you need to understand. So go through this video again to see what I did. So 3 is the minimum. The average utilization of 3, which is rho, is going to be equal to lambda over mu, which is 2. The LQ can be gotten from figure 7.12. That is the table that I was talking about, 7.12. or exhibit 7.12 from the book. From the book, if you go to the exhibit 7.12, the first column is rho, which is lambda by mu. So you go to 2 on the first column. Now you will see how many clerks. So you have for 1 clerk, 2 clerks, 3 clerks, 4 clerks. You may not have 1 or 2, but then you will see 1 for 3 clerks. So if you go to the row where it says 2 and then go straight across and go to 3, next to that 3 is the expected number of mechanics waiting. That means that number comes to if I go through that in that figure, it comes to 0.889. That's the number I get. The cost of 0.889 is going to be, I'm going to do it in the next video.